Okay, welcome back here. We're talking about Chapter 16, Electric Forces and Fields. There will be a quiz on this, so make sure you take some notes on it, review the stuff. There will be no new math here, but um, just like last time, there will be a review math problem or two on the quiz, so make sure you review some of the stuff we had previously covered, so keep that in mind. Okay, electricity, as we know, we use all the time. It's come a long way from Benjamin Franklin flying a kite outside an electrical storm to where we are now, but we use it all the time, and it's something that will not be going away. But hopefully this will give you a little more of an understanding of what actually is going on behind the electricity that we use. All right. Now, first thing we're talking about is an electric charge. Okay. Um, you guys have heard, I'm sure, that electricity is polar, so there are two kinds of charge. You either have a positive charge or a negative charge. Okay, so those are the two types of charge, positive or negative. Um, like with most things, opposites attract. So like charges are going to repel. So two pluses are going to push away from each other, and unlike charges are going to attract. So a positive will attract to a negative, and vice versa. Vice versa. So that should not be something that's too unfamiliar with you. It's the same way magnets work, actually. So the other thing about electric charge is that it is conserved. Okay, it's kind of like matter. It's not it doesn't go away. It can change forms, but it's conserved. So now you guys have heard of atoms before. Atoms are the big reason or the reason for this electric charge. Um, Inside of an atom, you have positively charged things called protons, uncharged or neutrally charged particles known as neutrons, and then negatively charged particles called electrons. Now, remember, inside of an atom, the protons are located inside of the nucleus. So we're going to put a plus there, a minus there. Neutrons have no charge. So if you draw a basic hydrogen atom in the nucleus, which is the center of the atom, you would have proton, a neutron, and then somewhere outside of it, the much smaller electron would be orbiting. Okay, I know that's a very, remember, electrons don't orbit like planets, but they're in an electron cloud outside of the nucleus. So those are the parts of an atom, and they contribute to electric charge. Now, again, electric charge is simply conserved. Okay, it's not created or destroyed. It is simply transferred. Excuse me. So it goes from one object to the other. Um, Now, this is pretty commonplace. You guys have actually seen this quite a bit. If you rub objects together, you can create electricity. All right, it's static friction. Actually, if you go down a slide, like um, if you go down it enough, you can usually zap somebody because the friction created between yourself and the slide is creating that static electricity. And what that is, what's happening there, is the the charges are jumping from one object to the other, and then one object becomes more charged than the other one. Okay? You guys have all done this probably with a balloon even. And so, hi everybody. So if you rub a balloon on your head, if you rub it on your hair, what's going to eventually happen is that balloon is going to collect enough charges from your hair to change the charge in the balloon. And then you should get an effect where you can get objects to stick together. Hopefully this works. Okay, these should repel because now they should have the same charge. Okay, if you do that again, you guys, I'm sure, have done the deal where you stick it to a wall. Okay, so there's a balloon stuck to the blackboard. Okay. Now, again, what happens in that case is the the electrons are what jumps across. There are electrons that'll jump across from atom to atom, from object to object, which makes one positively charged and one negatively charged. Obviously, if you add electrons, since they're negatively charged, you add electrons to one object, that's going to make, so if we have a balloon and my head, okay, if we are going to add electrons over here, the balloon is going to become more negatively charged, and I will become more positively charged. Okay, that's why when you do that, you get that static or that electricity feeling, or like that popping of static electricity on your hair. That's why the balloon wants to pull your hair with it. If you have longer hair, my hair's not long enough to do that. Okay, and opposites attract here. That's what ends up happening when you do that. The electrons, again, we're not creating a charge, you're just transferring it. You're just transferring that charge. So basically what happens is that charge is quantized. Well, we're going to get to that in a second. Another way to do this is a great static electricity experiment or project that was done. And it's called a van der Waals generator. I actually have one here. Might be able to hear it. Okay, that guy right there that you're looking at, the silver thing, is it's called a van der Waals generator. And basically what it is inside the tube that you see here at the bottom is it's a belt that's running round and round and round, and there are some brass wires inside of it that it's connected to. And it's just creating static electricity. And then the orb on top sort of omits that static electricity. The cracking, I don't know if you can hear that or not, is it's giving off static electricity volts. It's a pretty intense, it creates a pretty good charge actually. Excuse me, it doesn't create, it transfers a pretty good charge. So what I'm going to do here is I'm going to see if I can collect the charge onto this rod, and we'll go from there. I don't know if you can hear that or not, but it's crackling pretty good inside my headset, so I'm going to take that. Just kidding. Okay, but it's pretty cool. Okay, so as you saw, hopefully you could see that on there. The charge began jumping from the generator onto that rod I was holding. That's because the charge on the orb becomes so great that it has to get rid of it. It can't hold on to it for very long. It has to jump across. That's exactly why lightning happens, is because the charge inside of clouds becomes too great that it needs to jump across onto something else, usually the nearest object. Okay, now continuing on here, electric charge gets quantized. What that means is there's a fundamental unit of charge. Okay, and that fundamental unit is at the bottom here. E is equal to 1.602167 times 10 to the negative 19th C. Okay, C is coulombs. That's what charge is measured in. So if we were going to go on to math with this chapter, we would be using that, and we could quantify what the electric charge of an object is. Electrical conductors, you guys have heard of these, are things where an electric charge moves easily through. Okay, these are typically metals, all right? All of the wiring in buildings are typically done with copper because it's a very good conductor. Not the best, but a good one, an efficient one. And an insulator is something that an object or electric charge cannot move very easily through. Okay, for example, rubber or plastics, okay, Teflon. Those are all good examples of insulators. All right, charges can move through them, but not very efficiently, not very well. Okay, conductors, charges move easily through. Insulators, not easily. Um, these there's a couple of different ways that electricity can be transferred or objects can be charged is through contact or induction. Okay, induction is the process of charging a conductor by bringing it near a charged object. Okay, that's actually what was happening with the van der Waals generator and the rod that I made. Um, that you could see that I wasn't actually touching the orb, but there was a charge jumping across. Okay, that would be induction. Okay, that's induction. The same thing with lightning. Okay, lightning is induction. Okay, the cloud or the cloud, which is actually a charged particle with lightning, doesn't physically touch the ground or the tree that it strikes, but there's enough of a charge inside of the cloud that it needs to release it, and it jumps through the air into the ground or a tree, whatever the nearest object is. Um, Talking Coulomb's law here, again, we're not going to get into mathematics, but just some basic conceptual stuff. When two charges are near one another, they're going to exert a force on each other called the electric force. Okay, and the law states that electric force is proportional to the magnitude of each charge and inversely proportional to the square of the distance between them. Okay, so proportionally to the magnitude and inversely to the square of the distance. That should sound kind of familiar. So if you have two very large charges, they will have a greater attraction. And the closer they are, the greater the electric force is also. Okay, it's a lot like gravity. If the distance is greater, there's less electric force created. Okay, so adjusting the magnitude of the charge and the distance between the charges affects the electric force. The resultant force on a charge is the vector sum. Okay, now typically you don't have one or two objects that are acting on each other, so you would have to use vectors. And the principle of superposition is simply a way of adding those vectors up to get the resultant. So if you had a charge here and a charge here, and then another charge here that was bigger, your resultant force would probably be somewhere in that direction. Okay, because you would add the charges of all of them, and your resultant is the sum of all of those charges, including the direction. Okay, Coulomb force, again, that's the resultant electrical force. It is a field force, okay? Electricity is a field force, just like gravity. Okay, gravity was the other field force we talked about. It doesn't require physical contact to happen. Okay, that's again how the sun keeps us in orbit, because the
Tiana Stoop, please come to the office, and the plaid pillagers need their frisbee back, so please return the frisbee to the plaid pillagers. Corey Stork.
Okay, sorry about that interruption. Again, with field forces, you do not need to have direct contact with the objects. All right, like gravity, it's an attractive force. Gravity is always an attractive force. Okay, it's always attractive. But with electric force, Coulomb force, it's both. It can be attractive or repulsive. Remember, like charges repel and opposite charges attract. So if you have two charges that are, if I have a charge here that's positive and a charge here that's negative, the same rule applies. Okay, the same rule applies where the magnitude of the charges and the distance between the charges would give us our Coulomb force, but these objects are going to be acting in opposite directions of each other. Okay? They're going to be repelling each other and pushing them apart. All right? And the opposite would hold true for if they, oh, excuse me, I said that. These are opposites, so they would want to be going towards each other. Sorry about that. If they were like charges, they would push each other apart, unlike gravity, which is always an attractive force. Okay, now the electric field, this is the region where the electric force is detectable. Okay, like with the van der Waals generator, there was a certain distance I could get away from it that I couldn't feel the electric field force. All right, or the charge would not jump. But as the charge increased on the generator, the electric field got larger. Okay, I could be further away and still feel it. So that's what the electric field is the region where you can feel that. The electric field, the unit for that is called E. All right, that's the unit, big E, and that's basically newtons per coulomb. Okay, again, it's a force, so you got a newton in there, and it's per coulomb, which is the measure of electricity. Okay. Um, Electric field strength, okay, the strength of the electric field, it's always measured due to a point charge. And again, if we were talking or if we were going to get into some mathematical problems, we would include that in here. But that's basically a test charge that you could put in there. So here is our equation for electric field strength. Okay, E is equal to Kc, that is Coulomb's constant, times the charge, Q is the charge, divided by the distance. Now that should look familiar to you. It's very similar to gravitational strength. Okay, if you remember gravity, gravitational strength was equal to gravitational constant times mass 1 times mass 2 divided by radius squared. Okay, very similar equation there. Okay, that's it. That's all we've got. Sorry about the interruptions in there. So remember, there will be a quiz on this. No new math, but there will be some review math. And if you have any questions, you can ask me in class. Thank you.